we were speaking about the fact that 5G has a very diverse set of specifications, and the reason why I was telling this is to underline that we need a flexible infrastructure. So in the next slides, actually, we will discuss about some aspects, let's say, not always so much related, but several ways in which you can achieve some improvements or achieve a flexibility, adaptability using virtualization, okay? In general, one of the, let's say, more well-considered scenarios is the one of the mobile virtual network operator. So one of the scenarios that standardization is surely addressing, maybe with virtualization, which how I think, or maybe in another way, but they will need to solve the problem of enabling a company that doesn't have the infrastructure to operate a shared infrastructure with the true owner, at least. And for this reason, this is a big point also because there are, in the same scenario, there are also the over-the-top service providers that also are interested in having more control on the infrastructure where they deliver their services. So here there is some a selected part on how to achieve multi-tenancy in 5G networks. So practically, I refer to a working group of 3GPP that is called SA1 that provides these business scenarios. So for example, to have multiple core networks that share a common RAN, this is already available. It is already possible. I will show you which is the idea. But also there are other applications that go more into complex stuff, like common spectrum sharing, for example, as flexible as possible. So there are several degrees, or also to have multiple radio access networks that are that have a common core network. Maybe just close the door for. Thank you. It might be a little bit distracting. So that is an example of how currently it is possible to foresee a simple sharing of the infrastructure. So you have, in this case, we share the radio access network. So the base stations, there are two possibilities in the standard. One is this that is called multi-operator core network, where each base station answers to two different core networks, like this. And you see here the protocols that are used for the interaction between the base stations and between the packet core and the base station. There is another solution where the same happens, but through a shared mobility entity, the MME. In this case, if you can see, the system is a little bit more controllable because this device can decide which commands go to the base stations effectively. So it seems to be more effective at the moment because also in general, when you, in the current vision of network sharing, what is possible to do today is to have, if you are, the blue practically is the owner of the infrastructure. So there is a master operator network manager that is the one that controls. And all the requests to share the part of the radio access network that is shared, they go through the master operator. So this level of sharing is, if you want, similar, but here there is no virtualization in the system. It's like there's only a way to provide signaling, the same signaling that this operator would send to its own infrastructure can be sent through, like in the flow visor, if you want idea, to a proxy that decides how the radio network is operated. This is something that is already feasible, okay? With virtualization, one of the possibilities. Of course, I will show you several angles where you can have virtualization. If we focus on the base station, one way to have virtualization is to slice the radio access resources. If you see that is for those of you that are not familiar, the three small parts represent the upper part of the protocol stack of the node B, of the base station. They converge into a multiplexer that collects the requests. Then there is a hypervisor, that is, I don't know if you can see very well, it's the purple one. And then there are the actual physical resources. So basically, this structure is already foreseen in the standard, but there might be variants. So for the time being, this is what is written, which is called static reservation, which means that the spectrum is divided in frequency, okay? You see the frequency is here. And operator A will take the share on the top, operator B the share on the bottom, and each operator has its own, of course, MAC scheduler. So they have, let's say, reserved access to half of the bandwidth each. What they told me that it might be possible to be integrated in the most recent versions of the standard. Instead, is a solution that first was proposed by NEC, which is more flexible. This is actually what I mean by virtualization of the spectrum. So the idea is that you have both operators' traffic that you see on the top, but the difference is that you add a slice scheduler that decides how to provide the resources to the MAC scheduler. So first of all, the slice scheduler will check for example, the service level agreement or the contracts between the operators, and it will assign accordingly some of the resources. But those are not statically divided. They can be dynamically, because, for example, you can have an agreement where you have a minimum bandwidth that is guaranteed, and then if there is available bandwidth, you can go beyond. Or if someone is not transmitting, why should you waste that bandwidth, for example? So if you're sure that there is no traffic, why, for example, all this part is not used? Okay, so this can, if you see in the picture, the idea is to show you that you might have more flexibility in runtime optimizing the amount of resources that you give. And that is an example which is where you put network virtualization, but at the very low level. Okay, this is usually, sometimes it's called even spectrum virtualization, because what you do is practically, you generate a fake set of resources, and then you map them in the real resources, okay? So that is something that people in the standard told me that probably will come out for sharing. Then, of course, those are the hot subjects in the last months of standardization. So a big issue is the one that I was presenting you theoretically before, which is network slicing. So it seems to be clear that it will be useful to divide the network, or to partition the network into slices, because of the fact that you have to assure different QoS constraints to the different applications. So I say slicing, so I imagine something horizontal, but practically the idea is that you have a vertical, it's called vertical segment, so let's say a scenario for deploying a set of services, and you associate it with a specific slice of the network, so that you keep it isolated, so you can control the resources there, and you can also customize the services, okay, inside it. Then, of course, another thing is related to the fact that spectrum is not always utilized well. So to optimize capacity is not trivial, especially if you start to make slices. I will show you an example later on. Because on one side, you have to guarantee service level agreements, so you cannot play too much with the resources. But on the other side, you would like to achieve 100% utilization. You don't want to waste the resources. So these two things, they can fight between each other. So the idea is to enable some ways to share a bunch of resources that can oscillate dynamically, okay, to support peak traffic, for example, or things, situations that are very non-uniform in the traffic distribution. Then, of course, they are also working to the APIs, because, of course, today the cellular network is not open for services to look inside. The other thing, of course, there are other issues like more related to, let's say, the bureaucratic part, like how can I purchase the capacity for a specific time? Because there might be, maybe, I don't know, I'm organizing an event in a theater, and I would like to get connectivity, but I'm not an operator. I want just that service for 3 hours, let's say. This is something that it is foreseen as a possibility, so to find a way to have, let's say, short-term contracts. The other one is related, and this is, of course, very difficult to say, how you can multiply the slices, okay? Because there are situations in which the slices are associated, there are, in some pictures that you see in 5G, there is one slice for each of the scenarios, so practically five or six. Some people instead, they are thinking to what they call end-to-end slicing, so to have a slice of the whole network, including also the cellular part, but between the server and the client. That is a much more fine granularity level of slicing, so it means that for me, I will have at least one slice, okay, a complete slice for me, which would make it easy to have quality of service, because I isolate my slice, I get the resources that I need, there is no specific problem, besides the fact that how to scale up with millions of slices, for example, can be an issue. So this is, maybe you can have slices of slices, I don't know what they will do, because of course signaling is a big issue here as we increase. Here there is, I wanted just to show you, maybe rather than this one, you have the text that explains a little bit. This is basically the idea of how you can achieve multi-tenancy support in 5G. So the key point is this gray container that actually it's a processing operator that is called 5G network slice broker, because the idea is that if you see, they are very small, but you have two kinds of tenants, A and B, that are practically over-the-top providers. There is Google, Skype, and so on. Then you have another kind of tenant that can be another network manager, okay, which is the one tenant C here, the one on the right. The difference between the two is that if you are a network operator, you already have the interface for speaking directly with the network manager. So practically, you bypass the API of the services because you want to control the infrastructure, okay? Maybe you want to request bandwidth. Instead, the other will have a given API. Now, of course, it's being discussed which one will be. And it interacts through an abstraction layer that is called service capability exposure function. So that is the level that provides the view of the network, but for the applications, okay, for the services. And the way you allocate the resources in this point, in the network manager, depends on the slice broker. The purpose of the slice broker practically is to allocate or to activate also slices and the corresponding resources. So it will allocate resources, monitor the network. I will show you that several companies think that there will be the need for forecasting to understand whether the traffic is increasing, decreasing in each of the slices, and then to perform also admission control. Remember that if you are speaking about QoS, you always need admission control because you don't have infinite resources, okay? And then the other part is the previous one. So practically, the difference is only that there will be a modified interface for operating either directly with the infrastructure sometimes or through the radio access network manager. Okay, so that is what they are standardizing. So here there is a list of several modifications that will need to be done to the interfaces that already exist in the network. Type C5 is this one, and the other are this one and this one, because they need to support, for example, multiple IDs of the network, like you do in Wi-Fi, where you can send multiple networks. You will need to do the same, because you need this base station to inform that there are slices available on different networks, and so on. So for example, here there are some examples of the information that needs to be delivered. For example, also the starting time, duration of a slice, or of a request. What they propose is this structure. This is the corresponding diagram of the one that I was presenting before on LTE. Okay, it's the same, because here you have user equipment, radio access network. The names are slightly different, but here there is the definition. So you have, for example, the mobility management becomes AMF, which is this one. This is how let's say an external, if you want, the virtual operator will see the architecture of 5G, where all these functions can be virtual. Okay, so practically the green is how they are today. Okay, today you have the Node B, or in the recent standards the G Node B, which instead of evolved, I think it's general Node B. Then MME is this. So you can see that practically the idea will be that in each of the slices you can replicate through virtual functions the functionalities that used to be in an LTE network. Okay, so you will get your own virtual. If I want, okay, maybe I don't need everything, but if I want, I will have my access network functionality, which will be mapped into real base stations, into real spectrum, and also the signaling will need to be specified. Okay, these NG1, NG2, and so on are the ways these virtual network functions will interact between them. Okay. Here I left for you some. Here it explains a little bit what was the previous document. So here it is what you do. You can have, for example, user equipment using a single slice. So the green slice is dedicated to user equipment 1, and the red slice is for user equipment 2. And you can see that you share, of course, the radio access network. But you can also have, in principle, in the standard, a user equipment which uses multiple slices. Okay, in this case, you see that a part of the network is in common between the two slices. They don't mean that they are not isolated, okay, but they are logically overlapped. This is because at the moment there is not very clear what is the slice. So they allow this because maybe a slice, if a slice will be, each slice will be dedicated to each service, then this will happen to be maybe a realistic case. If a slice will be a whole set of services like broadband, vehicular, maybe this won't be very, very common, but we will go more in the previous case. You know, in the standards, a lot of things are left for, let's say, for implementation. So the standards enables this. So no one tells you that it will definitely be this, the final solution. Another thing that is used, here there's a lot of information in this slide, but what I wanted to underline is that, this is the first sentence actually, the idea of using slicing is similar to the process of selecting your cell phone provider. So the idea will be that when you turn on your telephone, instead of searching for your operator, the telephone will look for a set, because you can be subscribed to different services, a set of network slice selection assisted information indicators, which is this NSSAI. So what is interesting is that base stations will advertise the presence of the slices in such a way that it will be your terminal automatically in a transparent manner. I will not know I select this slice. It will connect to the services that I'm subscribed to, and with the corresponding signaling. Okay, here it shows you that, of course, depending on your request, you will select a different mobility entity. AMF is practically the MME. And then this will advertise the slice availability, and I will select the ones that I can, okay, or I want in that moment. So there are some more details here on the procedures, but basically, the novel, everything comes from that new indicator that is already standard because it is in these two technical reports that you can find cited here. Okay, so this is an example of how in the standard probably they will implement the slicing of the radio access network. Then there are other issues. So if you want to slice, there are other alternatives. Here is a small summary, so I just skip, we already reviewed it this morning. It's just a short summary of why you would like to slice the network. As you see here, a common way to believe slices will be provided is in terms of the scenarios. So one possibility, since every scenario will have a different requirement, a different set of requirements, and probably will require a different set of functionalities, one of the visions is that you can have one slice for each of, let's say, the 5 main arrows. So mobile broadband, this is vehicular to X, the automotive part, massive machine-type communication, critical communications, and so on. This could be one of the ideas, which is not only radio access network slices. Here you need to slice the network, okay? Because depending on your network, you will need different things. For example, here it's mentioned, if you see the keywords, of course, mobile broadband, it's the natural evolution of the network. So we will have more capacity, we will have higher coverage, whatever you want. But for example, automotive is different. Because you want, for example, maybe opportunistic device-to-device communication, so you want to have a way to directly transmit between two terminals without the infrastructure, maybe assisted by the infrastructure, but not directly through the infrastructure. You want, for example, we will spend maybe a minute on mobile edge cloud. So maybe you want the possibility to deploy some services as near as possible to the edge of the network, because low latency requires small distance, practically, and so on and so forth. So depending on the application, the slice will be built in a different manner. And that is where we have to recall the concept of SDN and network function virtualization. So on one side, yesterday you spoke about Cloud Run a little bit. That is the Cloud Run. So you have simple radio units, and the intelligence, so but this is the BBU is the baseband unit, so the processing part is detached somewhere else. But not only this, you might have some portions of the application layer that come together with these functionalities, and they are mapped also inside the radio access or the evolved packet core section of the network. Okay, and this is done, this is the same that we saw this morning. This can be done if we have support for network function virtualization. Okay, just as I was telling you, from the clouds to fog. So today, yesterday you mentioned a little bit this because it's very popular for applications like IoT, smart grid, even vehicular communications. So this is a theoretical vision of the cloud. So your services come from far away because you have cloud servers somewhere. What is the meaning of fog? Is that it is in the middle. Okay, the fog is, if you want, a sort of a cloud that is down to the terrain level. So what it means is that fog computing means that you could distribute services and resources everywhere from the cloud to, here they say the things, so to the real end of the network, okay? Fog means that there is no edge in the network, but everything is continuous from the cloud to the real hardware, if you want, in the hands of the people, which means that, exactly again, this is something that you want to do with virtualization, because you need to have the capability to move the functionalities, okay? So sometimes it's called mobile edge. It's always similar, mobile edge, fog. It depends how you define the scenario. But the concept is the same. If I want ultra low latency, at least I cannot do it if my system is in the cloud, because it's too far away. Okay? So for several reasons, I want to have an infrastructure that can allow me to move the services as near as possible to the user, because consider that if you are considering a vehicular scenario, you don't know where is the vehicle. I mean, you can know, but it continuously changes its position. So you cannot say, okay, I position my data center there, because so that in Albuquerque I will be interconnecting everything. Because if someone goes out, the service won't be fulfilling, for example, this constraint. By the way, another reason for, let's say, fog computing, or at least moving functionality around the network, is also connected to content delivery networks, which is a very sort of old concept, but today it's used a lot. So the idea that you bring the content as near as possible to the user, it's in the same sort of scenario. So as I can put the content nearer to the user, also I can put a service nearer to the user. But again, I need an hardware infrastructure, hardware and software infrastructure, that allows me to move these blocks. Okay? These are virtual nodes of the content delivery network. The idea is that, for me, it's the same if this block is here or here. The network will decide which is the best position. Okay? And if someone could say that, okay, maybe if you are doing video on demand or things like that, you can afford to have some delay, so you don't need 10 milliseconds, you can afford some seconds even. That is not true if you are speaking to control robots or vehicles, automated vehicles, or drones, for example. In those cases, either your system is completely autonomous, but that is very dangerous, okay, at least dangerous in potential, because usually the power comes from the networking of these devices, okay? The actual value is to control a fleet of vehicles together, not just one. Or a robot, for example, maybe it cannot have all its intelligence inside the metal, or a drone also that is very limited in terms of the weight. For this reason, here it shows you theoretically what I mean when we speak about fog or mobile edge. The idea is that you might have the intelligence to drive the car or to control the robot in a data center. But here the latency is too much. Then what you do is that in the fog vision, you can move the service, and that is where it's very similar to virtual network function management. You can move the service as near as possible to your object, so that the delay will be reduced, and usually also you avoid bottlenecks. Okay, there is another advantage that you avoid to saturate the backbone, because if everything runs in the backbone at the end, you will find a way to saturate. In this way, for example, you can put the service here, sometimes even on the item itself. Maybe it's better that the processing is done, but this is, let's say, a temporal decision. You can then take it away. So that is just to show you what could be the potential to use network function virtualization. So it's not only in cellular network per se, but everywhere you might have dynamic trade-offs between the performance and the network architecture or the network setup. If you want to change flexibly, this is one way where you can do it quite well. let me, I have a lot of slides on slicing the radio access network, but I think you got the message, so I will leave it for you to check on offline, because I wanted to save some time for the demonstration. Just to tell you what is in these slides. For example, we did a work with Stanford on because in LTE, usually the idea is that you use the full bandwidth through OFDM, but for a single cell. One idea is to reduce the interference is instead to use fractional bandwidth, so to select some subset of carriers and to use them in a better way to avoid interference. Because, for example, if I put two cells nearby, if you see the colors, the orange one will not interfere with the green that will come nearby, so you can improve the performance. The issue is how you split, if you can do it dynamically or not. So we did the work to understand which is the best way to split. So I just, you have the reference if you like. The interesting part is that we did it in the idea of Cloud RAN, so with considering that the intelligence is centralized somewhere, okay? And then there is another example. There is some mathematics for people that are accustomed. Another idea is that it can be interesting, again, with Stanford. We also implemented it. We studied a way to partition the radio access network, so the spectrum available to two different slices. But basically what is interesting in this work is that we were studying how many times you need to renegotiate your spectrum. So the idea was that we have two slices, and let me, maybe this one. We have two slices, and the slice manager allocates the resources within the slice. But there is another dynamic manager that is called dynamic spectrum level slicer that can change the percentage of resources allocated to each of the slices, okay? So that if someone is overutilizing a slice and the other is underutilizing the slice, you can dynamically change to avoid, you know, packet drops and so on. So the idea was to study how often you might need this, because the optimization in the red part can be long, okay? So you will see that, okay, there is some mathematical models. That is the model of the system. When we wanted to describe these red events, which are when I want to change or refine the allocation of the resources, because that can require some time. So it can be a time-consuming and bandwidth-consuming event, okay? And we saw that depending on, in the worst case, so if everything is completely random, you risk to have half of the times this requirement. So if both traffic are oscillating, you risk to be very often required to change the allocation. Instead, what I wanted to show you is this. This comes from a company operating in telecommunications. It's a proposal on how to build the network slice broker, okay? Again, here, if you want, I can give you the link to the paper, because we don't have much time. But what I wanted to show you is so how the broker can be built. The broker is the block that practically controls everything, because it decides when a slice can be accepted, and it decides how resources are mapped to that slice. So practically, what they say is that here there are the slice requests. There is, let's go direct to the admission control. So if you just turn on the system, the admission controller will start accepting slices, okay? And then there will be scheduled. So of course, if I own the slice, I will have my way to ask for resources, but then they are mapped into physical resources. The thing is that it also monitors the usage of the slice, so that it can drive a forecasting module that is used to understand or to predict in the short term how much that slice will be used. With the purpose to admit as many slices as possible, because if you do it without this forecasting and you do it in the hard way, you will probably waste the resources. Okay, so the idea is you fit your available resources based on the requests that come in, but knowing that there will be some holes, because maybe this guy, the owner of this slice, doesn't fill it all the times. What they propose, the interesting part is this one, is that after training, because of course it requires a little bit to understand the patterns, you see that you can increase the utilization of the link from, let's say, 75% to 90%, it's the red curve, with respect to the hard approach. So which is the price that you pay? Because it's good because you accept more traffic, so potentially you gain more, okay? The issue is this one, that they analyzed, of course, the forecast can fail. So in some cases, you might violate the service level agreement. So for a short amount of time, this might happen. And you can see, of course, they have their own proposal, it can be done maybe better. You can see that as you forecast for a long time, you start having a small percentage, because this is 5, so let's say it's 1%, maybe 2, but still you might have service level agreement violation. So this shows that maybe if the purpose will be to exploit more the resources, the service level agreements will need to be done more statistically, let's say not 99.99, but maybe 98%, okay? Because this would enable a very high utilization. If you want hard constraints, just on this working on this block, you can accept less traffic. Okay, the usual trade-off, you know, on admission control. Just a final thing before we go to the other part. Speaking about virtualization, an interesting work that was done by Eurecom is that, I don't know if you know this open air interface, Eurecom is a research center in France. They fully implemented LTE in software. So this is a testbed that also we are running in my lab. The interesting part is that this is, in my opinion, the best example of what you can virtualize, because practically everything, you don't have the base station, you don't have anything, you have just PCs. The only thing that you need, of course, is a suitable radio frequency platform to build the signal. But you can build a real network that can really connect to terminals, to actual smartphones. So this shows you that to make everything software is feasible, and it's also useful for making experiments, because you have full control on all the functionalities. For example, what we are doing in collaboration with the University of Tokyo, we are building, and we are almost to the final version. We are building an end-to-end slice. As I was mentioning before, the famous idea to connect the server provider with the service consumer. And for doing this, of course, it's not so, you have the reference if you like. The idea is to do it in the proper manner. So my colleague in Tokyo has very fast SDN switches, and that is how, this is the typical slice. You see two slices are the two green part. They are built using with the services that are the network functions are inside Docker containers. Here also, this is how the base station is built. So you have two, in this case two, but we can have even a single shared radio frequency interface. And then the node B is itself a virtual network function in Docker. So this is the switch that distributes the traffic, because this is connected to that one. Okay, this is the node B. So you must imagine this here. And so this is an example of how you can virtualize the whole network. Okay, we are finishing because the whole system is already working. We are just finishing because we want to use a single base station, a single real radio frequency part. So we are finishing to implement the slicing on the wireless, but it's already sort of working let's say with some bugs, but we can demonstrate that you can isolate two slices, so you can have two networks and control through, of course, then you can have the OpenFlow controller to manage everything if you want to reprogram it and so on. And here it shows you also how the control is separated by the data. Okay, you see, data is the blue, the signaling is the red. Of course, they are in the same box for commodity, because we didn't want to have 100 blocks. But they are split between the network functions for the control part and the network function for the data part. Okay? And that's almost it. Then there is a final example. Here there is the Cloud RAN, but I can skip it. I think you know it well. We made some experiments on how you can. The very last thing that I wanted to show you before going to the more practical vision is this 5G Norma project, where they are working on the deployment of virtualization, network function virtualization in 5G. So this is the reference model where you have data plane, control plane, and the MANO part, the management and orchestration, and the services. This is the general infrastructure. The useful part for you is that currently they are still working, so it's not the final result, but they are still working and they are defining which are the basic functionalities that can be abstracted at the data plane and the control plane. And they are doing it, what I found out, to a very small level of detail. Because, for example, the back functionality is a network function, okay? Or the PDCP is a network function, or, for example, you can see that a module for scheduling multi-tenancy access, a module for congestion control if you use the radio access network for the Internet of Things, for massive IoT communications. So this, I left it for you just as an example of real work, of really what they believe, because here most of the partners are industry and research centers, so it's not academics that, you know, you can feel we go 100 years in the future. This is something that they believe they can do, okay? And you can see the difference between what they plan. The blue is what they plan to modify to support additional functionalities, while, for example, the empty ones, these are dedicated for each slice. There are these, I think they are for managing the software-defined platform, and these are standard common control apps. So these are the control functionality for your network. Okay, so you can use it just as an example of what other people believe it can be useful to have. Okay, so before I move to the, let's say, hands-on part, I wanted to ask if there are any questions on this part. Okay, I went fast. The idea was to give you, let's say, some ideas here and there. If you are interested, please feel free to contact me or check in the slides. There is a lot of material. Okay, there are references. So now I would like to show you via an example, if some of you want to follow me using the virtual machine, on how easy is, if I will not fail, because it is always possible, how easy is to control a software-defined network, okay? So I think there is no questions, so let me sit down and I also have a bunch of slides for this. I will just show you the main ones because it's not, they are much more comprehensive. So I decided to have a third part of the third portion of the slides that I called SDN Laboratory. The purpose is to summarize the concept, but this I will skip because you already followed it 1 minute ago, and show you some basics of what SDN can do. So if you want to do it in practice, I sent this information in one of my emails, actually the only email that I sent you. The idea is that there is a software environment that is called Mininet, which allows to to emulate an SDN network. Of course, to run the virtual machine, you need some virtualization software. Here I was mentioning VirtualBox, that is the one that they suggest, maybe an X server and a terminal. Those are not mandatory. So here there are some, here there is some basic information on the different controllers that exist and so on, and the FlowVisor also software that I was mentioning before. But as I told you, this is something that is just a summary of what we described today. Okay, so let me skip and go. I also included for you, that is practically what I would like to show you today. So if I succeed until the end, to show you that you can have different slices of your network, and using a FlowVisor, you can configure it in such a way that, in my case, with two controllers, they see two different slices of the network. Okay, that is if I can arrive to the end, but feel free to ask me questions before, or everything anyway is written, so you can repeat it easily. This is the slicing concept, and of course this is the, there is a little bit of, let's see, some animations to help. Okay, so what we will use is Mininet. Just a small parenthesis on Mininet. Mininet is a network emulator. So as you know, that there are practically 4 ways to make a performance evaluation of a network. One is to use an analytical model. So it's more elegant. Usually it provides you closed form solution, hopefully, and you can reuse it very fast. Okay, if you have a model, but usually that is provides a very high level of abstraction. You must have to simplify things and so on. For this reason, at the other edge, there is actual measurement on a testbed. So another way to analyze a network is I build it and I measure it. This is, on the other side, is slow and very expensive. In the middle, there are 2 variants. One is network emulation and one is network simulation. For example, NS3, that maybe some of you will use, is a network simulator because it has the advantage that you can generalize or build a very big network very easily and run a very big experiment even fast. But some of the components of the simulator are still models. So for example, the channel is a model, but also the behavior of the system is to some extent a little bit abstract in some functionalities, because everything is usually reduced to generating events. Okay, the packet reception, packet transmission, errors, and so on. Emulation stays in the middle between simulation and actual deployment, because in an emulator, you are using a real protocol stack, okay, but you sort of multiply it by the number of devices that you want. So practically, you use the real protocols, but what is virtual is the links and the fact that all the machines usually stay in the same PC, okay? But it's the most near to the practice, so that is the reason why I use it, is because you can deploy actual software, okay? So if I want, today I don't have the time, but if someone wants to stream video, you can actually use VLC or the actual software and just connect it properly with the system. I will use the command line interface, which is very simple. So you must be super user, but the command of Mininet is mn to open the scenario. There is a set of parameters that I will just show you some examples. So when you open the emulator, what happens is that you build a virtual environment and within it virtual machines. The virtual machines can be controllers, switches, or hosts. And so you specify this, and you specify how they are connected. Then there are, I will show you, let's say, step-by-step command line usage, so everything will be not automated. But if you want, Mininet has its own language for building more complex scenarios, okay? This is what is mentioned here. I will not show you how to install because we can use the virtual machine, but if you want, there is some commands here. What we will see instead is some basic commands. Okay, here there are some examples, but there is later on a more significant set of commands. So usually you build, if you see, sorry, here, what you do is you start Mininet, you specify at least where is the controller. Otherwise, it will look for a controller on a standard port. Or you can run it using a custom topology or a pre-built topology. At the beginning, we will use very simple topology. Then, of course, you have monitoring commands, like you can check which are the nodes, which are the links. You can dump the information of all nodes. And the interesting part is that you can you can issue commands to all the hosts just by writing, for example, h1 means host 1. So you send a command to host 1, which is a Linux command, ifconfig, so you want to know how the network is configured. Or you can check the processes, like, you know, if you are familiar with Linux, is exactly Linux language. Of course, we will use this command ping because it's the easiest application to generate traffic. And also it's useful because ping checks for the reachability. So I will use it to show you when you isolate the network or where the network works. There is also another command, which is ping all. Ping all takes a while, but it tries to send the ping between all combinations of hosts. So you can check which hosts are connected to which other hosts. And then, of course, there are embedded in Mininet, there are some programs like iperf for generating traffic. There is this command for building links. You see, you can specify also the bandwidth if you want, the delay. For today, it won't be crucial, so we'll use general links. And you can also work through Python if you want. Okay, today I will not do it, but it can use Python. Or if you want, you can use, for example, in this example, you build two hosts, a switch and a controller, a link between the host and the switch. You assign IP addresses, and then you start the controller. So you can make everything automatic. Today I will do it manually because I wanted to show you the steps. But if you want, it's as a simulation. You can send a Python script that does everything. But you can do it at different levels. So you can do like this. So you can build a network object and then generate hosts and switches. Or you can also program in Python ways to generate a random topology with some rules. Okay. Then, of course, this can become as complex as you want. Okay, it's very flexible. So what I will show you today will be actually even simpler than this. But we first of all set up one network. Then I will show you that since the switch is dumb and at the beginning we don't activate any controller, the system will be not connected. Okay, so the switch will reject all the traffic because it won't do anything. I will show you how to simulate, let's say, a proactive flow insertion. So you can issue a command to the switch to program the flow table. So in this way, I will generate a working network. Then I will show you how it works instead if you activate the controller. Okay, the controller, Mininet is shipped with a couple of controllers. I will use the simple one, which is, it's called the learning switch controller. So it just implements a simple learning switch logic, but in a centralized manner. Okay, so the decision and the instructions are given by the controller. But the approach is exactly a learning switch. Okay. And then, if we have time, I will show you how you can slice the network. Okay, so that is basically what I want to show. This is how it. This is just a repetition. So the first thing to do if you didn't do yet, but I already did it, is to import the virtual machine in VirtualBox. So I will show you. I will just run it. Open that. This is VirtualBox. With this, the resolution is very small, so I hope that. This is a complete, of course, it's a complete machine that is virtualized. So there is Linux, and now it's starting up. Oh, it's readable. Might take a while. Okay. So usually the machine, without too much fantasy, the login is mininet. Okay. Also, so now mininet is not active. Okay. I'm just checking because there are two ways to use this. One is if you like, there is this. Let me show you one slide. I will use this approach. So I configure the virtual machine with two network interfaces, and one is an internal interface, so I can log in remotely. So it's better because I can have different terminals in an easy manner. An alternative for you, if you want, is to install in the virtual machine X, so the virtual environment. The command, the easiest way to install it is to this. If you are connected to the internet, to download xinit and lxde, and then start X. For I have both, but I will use this version that is even more interesting because I'm connecting to the virtual machine from outside. So let me check if. Okay. This is a command to see the interfaces. I think it's already available. So if I know where is the the arrow. I open simply a terminal and I connect remotely. Okay, so this is the terminal is here. Okay, now I'm connected, so that I don't overload too much that virtual machine because I can start and now I can open a graphical environment, so I can use extern, for example. So I will leave this as the mother, let's say, terminal, and this to issue commands. I hope that you can read. Otherwise, because it's very small. Anyway, maybe it is. No. Okay, but I will show you in the slides what I'm doing. Okay. So I don't know if some of you are you using this.
No, fine.
Okay, if you want, tell me if you have troubles. So that is the basic setup. So now that the system actually. We didn't start anything. We just have the virtual machine hosting Mininet, and I connected from remotely. So what we will do today, here there is a small summary of what we use. So we will use a simple OpenFlow controller. I don't have time to explain you how to configure it, so we will use the simplest one. But in principle, you can use whatever you prefer. Okay, there are controllers that have a very nice visual interface to configure the blocks. This one is just basic, so if you want, there is a verbose output, so you can check what it's doing, but very, very simply. But for the purpose, it's the same. Then we will activate one or more OpenFlow switches that, of course, are virtual machines in my system. We will use that command. Open virtual switch with that that is the OpenFlow control, where you can use to send OpenFlow messages directly to the switch, so you can mimic that you are the controller, okay? It's limited, but it can allow us to do a couple of interesting things. Then, of course, Mininet will be our environment. I don't think we will use this today, but there is iPerf if you want to check the bandwidth. Another thing that is very useful for those of you that are working in networks and didn't use it right until now is to use Wireshark. Wireshark is a tool that it's actually a protocol analyzer. It's open, so it's available to everyone, or multi-platform. It's very useful because you can track the packets. So I will show you when, of course we don't get into details, but I wanted to show you that actually there is, since you filter by the port of OpenFlow, there are a couple, not just that one, you can check the exchange of messages between the controller and the switches, okay? So that will be, at the beginning we will build this. So a simple switch with a few hosts. And at the beginning without the controller, okay? And then we will start building with this. So the command is the one that you see on the top. Let me run it. I leave it for you on that side. Let me close the other so that we have less windows. Okay, so I can run here Mininet. The topology here is a predefined one. It's called single tree. Then the other parameters, this is MAC, is for assigning each of the hosts a different MAC address. So it will be 00001 and 2. It's not, let's say, vital. Then the switch is OpenFlow switch, and the controller will be remote, but I don't activate it for the time being, okay? So when I run this, if you see here, for those of you that can read, but I can read it for you, at the beginning, it should add the controller, because in principle, the controller should be there, okay? I didn't add it, so, but it tells you that the system is expecting the controller to be available locally. The address, the IP address is the local address, on the port 6653. Then it adds hosts, H1, H2, H3, the switch, the links, and it configures the host, okay? For example, if you saw from the beginning, I can check which are the nodes. Okay, so the nodes are, in principle, the controller, but I didn't activate it yet. H1, H2, H3, and the switch S1. Then you can also check, there was, you can check net to see how they are connected. This shows you the port, the connections between the host and the switch. Then we can go on with the tutorial. Let me. So you have a slide that tells you what we did. Not much interesting. But for example, if I want, I can go to host 1 and see. Sorry, if config. As you see, it's exactly the same as any Linux machine. Here it tells me that it has this hardware address, this MAC address is all zeros and 1. It got the IP address 10.0.0.1 and so on. So here you can see if the hosts are properly configured. For example, host 2 will be similar, but of course different. Host 2 has the address 10.0.0.2 and so on. So this is just to check that the network is there. Then here there are some examples of what you can do. Another interesting thing that you can do is that you can open directly a terminal on a specific host. So I can say I want to have this one, okay? This is a terminal dedicated to host 1, so if I want to install something in one of the hosts, I can do this, or if I want to run something, okay, there is, you have all the commands that you want. Of course, I can check my configuration here. I can change it, do whatever I want. I want to underline, you can install real software. Okay, now I'm not, for avoiding issues, I disconnected myself from the network because, as I told you, there are security issues, so you never know what happens if you go out. But in principle, you can be connected to the rest of the internet if you configure the system. The last command that you see in the slide is, I don't use it now, is used for closing everything. So when you close Mininet, since it involves closing a lot of processes, if you just quit, it might happen that some processes remain active. So it's better that you send -c to clear everything, okay? I can do it, but no, there is no reason. We didn't change anything. But it's useful when you do, for example, for me, it will be useful later, because when I want to make another example, it's better that I'm sure that I deleted everything. Otherwise, it might be a mess. Then this is, for example, how I can connect to the switch, okay? So as it's written here, I open another terminal window. So from here, it's several of them, but they are useful to be separated. So here I can issue this command, which is to generate an OpenFlow command. And here I ask the switch to tell me which are its capabilities. Okay, so this is an OpenFlow command. You see here, it's OpenFlow features reply. It tells that it can have up to 254 tables, several buffers. It tells you which are the capabilities, so what it can do or what it can provide, and then it tells you the interfaces. Okay, these are the interfaces. They are default, so they assume 10 gigabit per second, things like that. But you can set up everything if you want. So this is just a monitoring command, just to see if you are connected. An interesting thing is to check if there are, which is dump flows. Okay, I'm following the slide on the right. That tells you if there is some flows written in the flow tables. But now, of course, there is nothing. Okay, so that is something that we can use later on to check the situation. And that is basically how we start generating some traffic. So I go on Mininet, so this window, and I generate a ping using 3 packets between H1 and H2. You will see that the answer is that the destination is not reachable, because up to now the switch is not configured. Okay, so of course here the slides are more verbose, if you like. There is more discussion. So actually I did it intentionally because I wanted to show you, and it is what is in this slide. Maybe I can increase the size of this a little bit. It should be like this. Maybe slightly better. But it's doing only this. Okay. So I think like this you can read. So the 2 commands there are used to issue 2 OpenFlow commands directly to the switch 1 in such a way that switch 1 will
we are doing actually proactively, we are pre-programming the flow table, okay? So this is if I'm a technician and I want my network just to work like this. I don't need the controller if I want, because if I know that I like this, then what I do is I go, let me open this one, in this window. What I do is I must be super user,